Steel Research Real Wonder.
You may not like graphs, but they're a convenient way of presenting facts, sometimes horribly familiar facts. This one shows the rise in the cost of living over the last 25 years. This graph is less familiar. It shows the rise in the cost of electricity over the same period. Why graphs for cost of living and of electricity? After all, this is a film about steel. But look again. The cost of living up 200%. Electricity only up 94%. And this is where steel comes in. On this site are 3 generations of power stations spanning 40 years. Each in turn has used steels that were successively developed to stand greater pressures and to work at higher temperatures. In a typical station around 1927, maximum steam temperature was 420 degrees. Maximum pressure, 600 pounds per square inch. And the thermal efficiency was only 23%. Output was 42.5 megawatts. By 1957, steam temperature had risen to 525 degrees. Maximum pressure had increased 2.5 times. Thermal efficiency was up to 32%, and each set had more than twice the output. In a typical modern station, every single factor has advanced again, though each improvement today demands enormous technical effort. There have been considerable advances in power station design, but the most important single factor has been the development of many kinds of better steels and of improved ways of forming them. Turbine blades are a critical component. The greater the steam temperature they can stand, the higher the generating efficiency. The temperature at which such steels are forged is critical. Several time-consuming reheats are required to achieve the final shape. One way to solve the problem is still at pilot plant stage. It's a method of feeding heat into the ingot while it's actually being forged. Banks of powerful radiant heaters balance the heat losses from the ingot so that it can be maintained for the required length of time at the correct forging temperature. If the process is proved to work on a production scale, costly and wasteful reheats will be unnecessary. It should be possible to make turbine blades to stand higher temperatures, and this would mean more electricity from a given amount of fuel. Tubes for steam superheaters are another critical power station component. They have to work at red heat. At this creep test laboratory, inside these banks of heaters, hundreds of different steels are being tried out for the next generation of power stations. Steels with different metallurgical structures, steels made by different methods. Some of the test pieces have been at high temperature under heavy load for as long as 15 years. A telescope and mirror system enables elongations of a few millionths of a millimeter to be observed. From time to time, deep within its heater, a test sample will break. It may be after a few thousand hours, or many years. specimen is studied to discover why it broke, to see if there's some way to improve its properties. Here the fault is clear, but very hard to avoid. A minute scrap of impurity that got into the steel and was rolled into a laminar form. The million-volt electron microscope is one of many tools that are used in the study of high-temperature steels. A steel's behavior depends both on its physical structure and its chemical composition. To optimize both demands intensive multidisciplinary research. This is a Perspex model of a different kind of tube, one designed to stand a different kind of strain. Tubes are versatile, efficient, and economical for standing a variety of different types of stress. When the winter rains come, Celtic supporters can thank tubes for giving them reasonable comfort, without any pillars obstructing their view. The strength of such tubular space frame structures depends on the efficiency of the joints. A lot of work is being done to find the best design. Increasing loads, particularly when unbalanced, can eventually fracture any joint. The question is, where will it break? As a result of such research, steel space frames are used to roof huge unobstructed spans, bigger than a football pitch, such as a jumbo jet hangar. And steel sheet is perhaps the most economical way of enclosing such large areas, particularly sheet which is coated inside and out to resist corrosion. The steel is first zinc coated, then the outside is intimately bonded to a plastic film. This material can be used wherever the customer requires the cheapness and formability of sheet steel, plus the decorative qualities and weather resistance of plastic. This pilot plant was the start of a new steel coating process which we think will be a winner. Pure aluminium powder is sprinkled evenly into an electrostatic field which accelerates it towards the steel strip. The coated strip is first heated and then it's rolled. This bonds the aluminium permanently to both sides of the steel. The pilot plant worked with 4-inch strip. The next stage was to try the process out on 10-inch strip in a really big pilot plant. This produced enough material for customer evaluation. Reaction was good. L-FAL, as it's called, gives really excellent corrosion resistance at a lower cost than any competitive material. So, 10 years after the basic research started, we commissioned a production plant. Its output is 100,000 tons a year, and it can produce strip up to 54 inches wide. If the coating can be made of powder, why not the steel itself? A man and some powdered steel could be the start of a revolution in the industry. Squeezed between rolls, the powder is compacted into a strip. At this stage, the strip has very little strength. It has to be handled carefully. But even early experimental batches had enough cohesion to be floated on a cushion of compressed gas through a temperature-controlled furnace. This was an achievement in itself, But although this kind of research may be a technical success, only the years will show whether it will lead to an economically viable way of producing steel strip. Coming out of the furnace, the sintered, compacted powder is strong enough to be coiled. It's then taken to be cold rolled. A succession of passes through the rolls produces the finished product, in this case, top quality stainless strip. Most steel is hot rolled and the ingots are brought to the right temperature in soaking pits. There are often over 20 pits. Some will be hot, some cold, some charging, and just one will be feeding the mill. The soaking pit controller has to maintain a steady supply of ingots, not overcooked, at just the right temperature for rolling. It's an extremely complex scheduling problem, and his aids are often rather rudimentary. With this scale of operation, any major changes are extremely expensive. So as an experiment, a mobile computer has been brought in to see if it can improve the controller's efficiency. If the computer can show a worthwhile economy, then a permanent installation can be planned. A touch of the finger communicates with the computer. And it's possible for the controller to try experiments. For example, how would the schedule be affected if pit 02 was rolled before pit 03? From the moment the steel was poured, every significant fact about its progress through the mill has been fed into the memory banks of the computer. It's possible to obtain instantaneous information about the state of any cast in any soaking pit. The computer is designed to be a tool to help the controller. The object of the exercise is to see if, with its aid, he can keep R for rolling visible for a higher proportion of the day than he can on his own. For a high-speed repetitive job like tube inspection, it's better to cut out the man and automate the job completely. The operator has only to control the flow of tubes through the equipment. Rotating ultrasonic probes scan the tube for any possible defect. A continuous printout on a chart pinpoints and identifies each individual imperfection. This, for example, indicates a laminar non-metallic inclusion. Rail testing equipment is not yet at such an advanced stage, though it looks promising. In this experimental rig, ultrasonic pulses are fed through water jets. The trace on the cathode ray tube is found to correlate nicely with the deliberate faults cut into the side of the rail. The increasing size of ships demands plate of greater thickness and strength, but it must still be easily weldable. One technique being developed to achieve the required strength is allowing partly rolled plate to cool and then finishing rolling at a lower temperature. Controlled rolling, where each stage of the process is carried out at the ideal temperature, can achieve the best combination of properties for heavy-duty plate. Another line of research is aiming for a different balance of qualities, for toughness and resistance to impact, allied to easy weldability. In this pilot plant, steel plate is rolled at a precisely controlled temperature and then rapidly quenched. The resulting product can stand the roughest, toughest industrial use. A problem of a totally different kind cropped up when this steel-making vessel was being run in. It was found that some of the water cooling tubes in the hood were springing leaks. The tubes were being burnt through, but why? Within days, a scale model had been made with air bubbles simulating the circulation of water and steam. Injecting a dye showed that in the up pipe, where steam should have been rising, in fact, water was descending. Having discovered the fault, it was fairly easy to solve the problem and get production going again. A considerable effort is devoted to introducing totally new products. Sound-deadened steel, for example. A lot of work is routine. Someone wants to know how many times this steel sample at red heat will twist through 360 degrees. Rather staggeringly, the answer is over 50 times. But most research involves using every conceivable physical tool and mental agility to foresee future needs and meet them as they arise. For steel is not one material, it's many. Some steels need great strength, some resistance to corrosion. In some, easy weldability is vital, or strength in compression or tension, or springiness, or resistance to high or low temperatures. It's the job of the research worker to combine several of these qualities in one product. Steel can influence the price not only of electricity but of almost everything we buy. To keep the cost of living down, we need the right steel for the job. To produce this efficiently and economically is what steel research is all about.